Hello everyone. In this lecture we will be going over 1993 USAMO problem number 5. Here's a view of this problem. We are given a sequence of positive real numbers A0, A1, A2 and so on, and we know that these numbers satisfy this following set of inequalities for all I. Given that, we would like to prove the following inequality here. So what I will do is, first let's, in order to simplify the arithmetic, I will make the following definitions. So let's call the sum of the AI's from I equals 0 all the way to n as S, and also let P be actually the product of these A sub i's from 0 to n. So what I would like to do therefore is we would like to show that show that in fact S over n plus 1 times S minus A sub 0 minus A sub n over n minus 1 is greater than or equal to S minus A sub n divided by n times S minus A sub 0 divided by n. So that's exactly what we want to prove. So let's start with this right hand side, and I would be making the following trick. I can represent the right hand side alternatively as especially the first one, A sub 0 minus A sub 0 plus S minus A sub n times, and I will just leave the second term as it is. And from here what I will do is I will do some algebra here. So I will consider this expression here as 1, and I will just multiply out these two terms. So therefore I will have minus A sub 0 times A sub 0 will give me minus A sub 0 squared. Obviously there will be a big division sign here, and the denominator will be n squared. And then I will have A sub 0 multiplied out with this whole thing with a minus sign, and then this A sub 0 multiplied with S. So let's actually start with that one, S minus that one here. So we have S minus A sub 0 minus A sub n, and we still have also this term multiplied with that term here. So therefore we have plus S minus A sub 0 minus A sub n times S. Okay, so from here we can make some simplifications. Obviously we would realize that this A sub 0 times minus it would be plus, so therefore this A sub 0 and this A sub 0 square would cancel out. In addition, this S and this S would cancel out. So therefore what I would have remaining on this expression would be A sub 0 minus minus, so A sub 0 times A sub n, A sub 0 times A sub n, plus this term here, S times S minus A sub 0 minus A sub n all over n squared. So what I will do next is that I will just split this into two terms, it's possible, and then move the right term to the left hand side. But in fact, so let me just do it first. So we have, oops, sorry for that. So I'm going to go ahead and split it as I promised. So I will put a plus sign here. So A sub 0, A sub n over n squared, and then we have also the second part, S times S minus A sub 0 minus A sub n. Now check this out. On the left hand side we have this product here, S times S minus A sub 0 A sub n, and we have it on the right hand side as well. So if I move this whole expression to the left hand side, we have the following equivalent representation. I can factor out this product. So I have S times S minus A sub 0 minus A sub n, and then on the left hand side I have 1 over n squared minus 1 and I would have minus 1 over n squared coming from the right hand side. I would like to show that that expression is actually greater than or equal to a sub 0 times a sub n over n squared. Obviously, what I need to do is I need to find the common denominator here, and then I will realize there will be some terms cancelling out. So therefore, let me, in this given space, let me try to, let's just, okay, let me just use the same page. So let me just create some space here. I still have the expression that I would like to prove on top here. That's what I want to prove. So therefore, let's equivalently write that this expression here. So when I have the common denominator, that would be n squared minus n squared plus 1, so the n squares will cancel out. So therefore, what I will have remaining on the left hand side would be this very nice expression, all divided by n squared times n minus 1 times n plus 1. So I'm just factoring out that squared expression greater than or equal to a sub 0 a sub n divided by n squared. But the n squares will obviously cancel out, and after I do some cross product here, I can confidently do it because I know n is greater than 2, greater than or equal to 2. So therefore, the equivalent expression that I have that I need to prove turns out or reduces to the following form: s minus a sub 0 minus a sub n greater than or equal to n minus 1 times n plus 1 times a sub 0 a sub n. So that's the equivalent form that I would like to show. So let me move this expression to the next page, and let's have a clean page open. So I have, let me rewrite this expression again. So I would like to show the following. So I still need to prove this. So we were able to reduce this given inequality, and so what we needed to prove, into another form, which is I feel is more tractable, and so that's what we want to prove up here. Okay, so that's the thing that I would like to show. I will go ahead and apply AMGM to the two terms on the left hand side separately, and hopefully so let me write that down. Apply AM, the arithmetic mean geometric mean inequality. So let me start with the left hand side and see if I can simplify the things. So therefore, when I apply these to the left hand side AMGM, what I would get is I still have so s minus a sub 0 minus a sub n. That thing is greater than or equal to by AMGM. So remember that s was the product, so therefore the sum, so therefore the sum will become a product, and I will have, because I have n plus 1 terms here, and there will be a product n plus 1 coming out, and then there will be the p here, so the sum will become a product. However, I will still have to take the 1 over n plus first power, and then regarding this term, there will be because there are n minus 1 terms in this sum, so this will translate into p over a sub 0 a sub n, and that would be raised to the power 1 over n minus 1, because that's how many terms we have. And that's what I want to show. I want to show that this expression is actually greater than or equal to, so greater than or equal to what I have here. So therefore, I do have an actually, let me just do it on the next line, so that would be more. So therefore, the problem first reduced from this form to this form. Now I have further reduced to a more interesting form. So I need to show that s times s minus a sub 0 minus a sub n is greater than or equal to this expression here. Oh, sorry, my bad. So let me just do it again. So therefore, I showed that, so this expression, if I can show that n plus 1, p to the power 1 over n plus 1, n minus 1 times p over a sub 0, a sub n, raised to 1 over n minus 1, if I can show that that expression is greater than or equal to the right hand side up here, that proves that's a stronger result, because, well, I know that my left hand side is already greater than this. So if I can show that this is greater than this, which is the right hand side here, that would be proving that the left hand side is greater than the right hand side. So I realize that the n plus 1s are cancelling here, and the n minus 1s are cancelling, and I'm moving the a sub 0, a sub n to the right hand side. Further, my task is now simplified. The problem reduces to proving, so I can now expand that p notation here as the product. So what comes out here is that the whole thing becomes you can write it in so let me actually do it in 2 steps. So we have the square root expression here, not the square root, actually n plus first root of a sub 0, a sub 1, a sub n, and we have another power, a root, n minus first root. This one though is missing the a sub 0 and a sub n, so it starts with a sub 1 all the way to a sub n minus 1, and we would like to show that this thing is greater than or equal to a sub 0, a sub n. Now what I will do is I will expand these things and move the a sub 0 and a sub n to the right hand side, and then take the n squared plus minus 1 over nth power of this, and therefore this reduces to showing that a much more simple form, a sub 1 squared, a sub 2 squared, all the way to a sub n minus 1 squared is greater than or equal to a sub 0 n minus 1 times a sub n minus 1. So we were able to reduce the problem here in the question into an equivalent form, which is much more handsome. So let me move this expression to the next page, and then let's figure how to prove this result. So let me rewrite it here. So as I said in the previous page, we were able to reduce the problem into this format here, and now that's what I want to prove. But I've been given a condition here that I have not used so far, and it is this set of inequalities which holds for all positive integers I. So what this means is that, so let me write these conditions. It's given that, or let me say we know, now I'm proving this reduced form now. So we know that, well, if I plug in 1, a sub 0 times a sub 2 is less than or equal to a sub 1 squared. If I plug in 2, I know that a sub 1, a sub 3 is less than or equal to a sub 2 squared, and so on. Let me write down a few more terms. That would be a sub 3 squared, and finally I will have something like a sub n minus 4 times a sub n minus 2 less than or equal to a sub n minus 3 squared, a sub n minus 3, a sub n minus 1 less than or equal to a sub n minus 2 squared, and finally one more, so a sub n minus 2, a sub n less than or equal to a sub n minus 1 squared. So we are given this set of inequalities here, and from here's my objective. Let's first observe that by multiplying out these expressions here, and remember the a sub i's are all positive integers, so each one of these set of inequalities are all greater than or equal to 0. So multiplying out these inequalities will not change the direction of these inequalities. So observe that, so when I multiply all this out, I have just one a sub 0 term. So therefore, let me create this column here, multiply all inequalities. So by multiplying all inequalities, I get the following expression. So I realize that I get a sub 0. And how many a sub 1s do we have? Only one again. So a sub 1. I'm just multiplying out the left-hand side first. And we realize we have two a sub 2s. So therefore, a sub 2 squared. And then we will have two a sub 3s, and so on. Until this one, a sub n minus 2 will appear twice. That's the last term which will appear twice. and then a sub n minus 1 and a sub n will both appear once. And that whole thing is less than or equal to this long expression a sub 1 squared, a sub 2 squared, all the way to a sub n squared, or sorry, a sub n minus 1 squared. After I do all the simplifications, so obviously we will have the a sub 2 squares cancel, a sub 3 squares cancel, all the way to a sub n minus 2 cancel. So what we will have left on the left hand side would be, obviously the a sub 1 will cancel with this square here, and the a sub n minus 1 will cancel with this square here. So this will imply that a sub 0 times a sub n is less than or equal to a sub 1 times a sub n minus 1. Likewise, I can continue, instead of multiplying all the inequalities, I can multiply all inequalities except the first and the last. Let me do one more example here. So multiply out again, multiply all except first and last. So in that case, I'm not multiplying the first and the last, just the ones in the middle. So I will have only one a sub 1 appearing in the product on the left hand side. I will again have only one a sub 2 appearing. A sub 3 will appear twice, once here and then once in the next. Remember, I'm not using the first and the last ones, so therefore a sub 3 will appear twice. All the terms from a sub 3 squared all the way to a sub n minus 3 squared will appear twice. A sub n minus 2 will appear once, and a sub n minus 1 will appear also once. That whole thing will be again less than or equal to the terms between a sub 2 squared all the way to a sub n minus 2 squared. So after simplifying, realizing that all the a sub i's are greater than 0, so no problem in simplification, all these square terms, the things in the middle will all cancel out. The a sub 2, the square will cancel out with this one, the square here will cancel out with this one. So on the left hand side, this will imply we will have just an a sub 1 and an a sub n minus 1 remaining, which will be less than or equal to a sub 2 and a sub n minus 2. But notice that a sub 1 times a sub n minus 1 is greater than or equal to a sub 0 a sub n. That implies that a sub 0 a sub n is less than or equal to a sub 2 a sub n minus 2. So therefore, by proceeding in the following way, or you can say by induction, if you will, either way, you can find that for all I, let me add some space here, so we're about to come to the end of the question. So what I'm claiming now is, let me write it in green, so for all I from obviously from 1 all the way to n, we therefore know that, or let's not use any logical symbolism, but let's just use just pure observation. So obviously we would see that a sub 0 a sub n will be less than or equal to a sub 1 a sub n minus 1, which is further less than or equal to a sub 2 a sub n minus 2, and so on. It will proceed like this until the last one will be a sub n minus 1 times a sub the total is n, so therefore that's what we are going to see. So therefore each one of these expressions in this sequence will be greater than or equal to a sub 0 times a sub n, and that's the crux move. So we will just write these and then multiply them out separately. So therefore, so what I mean is that I know that a sub 1 a sub n minus 1, so let me write it here. So is greater than or equal to a sub 0 a sub n. A sub 2 a sub n minus 2 is also greater than or equal to a sub 0 a sub n, and I can continue in this fashion, obviously, a sub 0 a sub n, all the way till the last line where I have, let me just write down the last two lines, a sub n minus, actually a sub just 2 in that case, sorry for that. A sub 2 is greater than or equal to a sub 0 a sub n, and finally a sub n minus 1, a sub 1 is greater than or equal to a sub 0 a sub n. So if we further one more time multiply out all these inequalities, again all the a sub i's are greater than 0, so that's possible. It will not change the direction of the inequalities. So sorry for that. Yeah, as a result, this multiplication, the left hand side will give us immediately the left hand side of this expression, and the right hand side we have n minus 1 powers of each one. Well, actually we have 2 times n minus 1 powers of each one on the left side, a sub zeros and a sub n's, but again on the left hand side we have also you will see 2 of them appearing at the same time, so therefore the product will immediately lead to this result up here. So therefore that solves the problem. We were able to reduce the problem given in the question into a simpler form, and then use the condition given in the question, namely these set of inequalities, to ultimately prove the given result. And ultimately you can make an induction step saying that this will hold for all positive integers n. So that solves our problem. Hope you enjoyed it. See you in our next video.